Our next presenter is Mr. Mike Gaffney, Senior Engineer for Navis Energy Solutions. The title of his talk is Energy Efficiency on Fishing Vessels, Preliminary Results from Alaska Fishery Development Foundation, Fishing Vessel Energy Audit Project, Baseline of Energy Consumption and Cost and Methods to Reduce. Mr. Gaffney is a graduate of the United States Merchant Marine Academy. His experience includes technical fleet management, manager for 11 contract-operated MSC ships. He's been port engineer for several shipping companies and served as chief engineer for 8 years on numerous ships. Over the past 8 years, Mr. Gaffney has been focusing his efforts on marine energy management. This includes work as lead energy auditor on Navy, U.S. Coast Guard, MARAD, NOAA, and commercial ships, both domestic and abroad. He's a certified energy manager, certified energy auditor, and certified power quality professional. He is presently a senior engineer with Navis Energy Solutions and holds a licensed chief engineer of U.S. Coast Guard. Mike is a returning from Greenboat 1 and 2, and we're very pleased to have him back to get an update. Mike?
Thank you very much. Okay. All right, well, thank you so much for joining me today. I know I had some wonderful presentations today. I got to have the energy of the previous speaker and see if I can talk as fast as Catherine here. I don't know if I can live up to either one. But today, we're going to talk about the energy efficiency, just a brief overview of my perspective of it, and then go over the project that I'm doing now with the Alaska Fisheries. It's run by Alaska Fisheries Development Foundation. Julie Decker is the executive director there. Catherine, you need to talk to her one of these days. Interesting conversation. And then it's also with the Alaska Longline Fishermen Association. Dan Falvey up there. Dan Falvey up there. He just handed me this huge Alaskan king crab. He like walked out and handed it to me. The thing was monstrous and it was reaching for me. Oh my God. Anyway, the dangers of doing energy audits in Alaska. And then finally, the analysis tool that we developed over the past few years as part of the project. And then from that, we developed the baseline and had a better understanding where the energy goes. We tried a couple of ECMs, energy conservation measures, and we'll talk about them. So to start off with is the culture aspect of it. We had a lot of good presentation, a lot of people talking about the culture. And for me, that seems to be the hardest aspect to bring about change, but yet it has the largest benefit that we see. I mean, simple things like turning off the lights. I've done audits for the ships and ports, and it's 25% of the energy. Why? It's like impossible. It is possible because they're all turned on 24/7. And then I go on a lot of these ships too, and you see the air conditioner set at 42 degrees, and yet over here the heat is on. I did retro commissioning on the MSC ship, and we did some chill water reset trying to get the air conditioning turned off. By the way, it's the middle of winter. And so I raised it from 33-degree chill water temperature up to 44, and they complained that the boat was hot. I was like, well, it's 40 degrees outside. It shouldn't be hot. You're in heating mode. So I go and I find the air conditioning on the bridge set for 40 degrees, and the reheat's at 90. So when I decreased the capacity of the air handler, the reheat then took over and started to warm everything up. So instead of reducing the chill water temperature and increase the air conditioning in the wintertime, I just went up and I turned the heat down. I mean, it sounds easy, but I went on, there was like 4 or 5 ships of the same class, and everyone was set up the same way. It's not that these people aren't good people or want to do the right thing. It's just how it's always been done for, I swear, decades sometimes. And overcoming this tribal knowledge can be difficult. And I really enjoyed Peter's conversation today, too, and the success he's had with the culture. I thought it was inspiring. So here's a retro commissioning that I did on a ship that was in port. Again, awesome chief engineer on there, very sharp crew. But they've been doing stuff the same way for a long time. So here's where I got on the ship, back here in the beginning of somewhere around the 8th or so. And then we started going around and just adjusting the equipment they're on board that they were running, turning things off that weren't absolutely needed. And so we reduced the load 40%. And that's just all culture. That's all policy driven. but it's doable. So then we have this, the cultural aspect is one part of energy efficiency and how we can reduce our energy cost. And my focus is always on cost because that's where we talk about customers and what they want, and it's money that drives it, at least from what I've seen. So if we take a look at energy efficiency from a technical perspective of it, we're looking at how efficiently are we using that energy. In the case of the ship, the bulk of our energy is coming from fuel, right, when we're out at sea. That fuel has a certain amount of chemical energy in it that's available for us to convert to another form that we need. The main efficiency that we see on a ship is how efficiently we convert that energy from one form to another, or minimize the losses, or utilize the losses during waste heat or recovery. So if you look at the simple case of the Navy ship, we have a lot of the military around. I do a lot of work with the Navy. Gas turbines, low loaded, the way the Navy typically runs them, maybe they're 15% efficient, maybe 25, to load them up a little. And because they're always lowly loaded, they have so much redundancy. So if you think of it in that aspect, about 75% of all the fuel that's carried on board is converted into waste heat. It all goes into the ocean as heat loss for cooling or up the stack. 75% of it. Imagine if we could use more of it, we don't have these little fuel tanks. But the reality of it is we have losses whenever we convert energy from one form to another. So in order for us to minimize it, I think it's important for us to understand where those losses occur. And that's part of energy management. So in this case, we take fuel in as chemical energy, we put it into our energy, we burn it, we convert it into torque energy coming out, then we transfer the energy down through the tail shaft, and then convert that torque energy again into forward thrust energy. So we can minimize the conversion process as well as minimize the requirement through better lubricants, better hull coatings, proper trim, etc. So this inefficiency in this conversion process, it continues on our electrical systems, on our auxiliary systems. In the case here from the torque energy coming from the engine, that we already had all these losses, now we have to convert that into electrical energy, which now we have to transmit through our wires. Then we go into our transformers, which we have more losses as we're converting energy from one frequency to one voltage to another voltage. And then finally we go to our end users. So for our pumps and motors, now we have to convert back again from electrical energy to torque energy. Now we have to convert that torque energy back into a fluid movement. And all these things have losses. And when you start adding them up, I think it's pretty easy to see that these losses can be significant. So how do we improve this? This is where the energy efficiency equipment comes in line. My career, most of it, I've been doing this for over 30 years now, at least working on ships. Always focused on the actual capital cost of the equipment, never actually on the amount of energy that it used. For something simple like a motor, transformers, even lighting, it's like 96% of the life cycle cost is energy. Yet when I was fleet manager, when I was chief engineer and port engineer, my budget was all about maintenance. I didn't care about the energy because it didn't affect me. And so I focused on that little sliver of the life cycle cost that had to do with the purchase and the maintenance, and I just let the other 96% of it go by. It wasn't actually when I was fleet manager, I got more into the energy side of it. But most of all my career, I did not do what I'm preaching now. Lessons learned. So on our project that I'm working on currently is the fishing vessel energy efficiency project up in Alaska. We started this a couple years ago through AFDF, the Alaska Fisheries Development Foundation. And they wanted to take a look at how are fishermen actually using the boats and what can we do to help reduce their energy cost. And so for phase one, we actually did energy audits on 12 fishing vessels. And then we so far just finished 6 more vessels in Sitka. I just came back from Alaska. And I'm heading there tomorrow morning. I'm actually going to Homer to do another 6 vessels or so. There's a picture of me in there and some of the metering that we're measuring, collecting all the data. So the purpose of it, or how we approach this, is what we wanted to do is build this library where it cataloged the typical cost that the fishing vessels had. And so we went on, we put our meters everywhere and collected all the costs. And that was to establish a baseline of where all this energy is going and the cost of it. And then from that, our baseline that we collected, we would say, okay, here's our high energy consumers, and we need to take a look at that and see if we can come up with some ECMs and a way to actually reduce the cost. So in order to have this baseline in a format that the fishermen could use easily that was relevant to them, we developed this energy analysis tool where the fishermen could go and fill it out and fill in their particular boat or a boat similar to one that we did, so they now have an idea of what their cost is to run that motor. How do you know if you want to upgrade that motor to a premium efficiency motor if you don't know what your current cost is, if you don't know what your current consumption is? So it's one of the things we set out to do, is give the fishermen a tool so they can perform these financial analysis so they only pick the items that are most cost effective first. So we set out, we actually put strain gauges on the propeller shafts, and we measured the actual amount of power it takes to move boats of different hull forms through the water. We haven't done one of those real ugly ones that Catherine brought up. It's just frightening to see that. But it is on the list, though. It would be interesting to see it. So typically, the curve there, you'll see about 6 knots or so, which they were typically running, 5, 6 knots on the transit. The boats hardly take any power at all, like 10 horsepower. And we're seeing some of these running up, with 300 horsepower engines. There's a philosophy, the bigger the better. And it's absolutely not true. I mean, the fishing boats are like perfect candidates for hybrid drives and electric drives. And I think the future, that's where it's going to be. And then we took a look at consumption because we wanted to quantify for the fishermen, well, how much does it cost me to run 6 knots compared to 8 knots? How much does it cost me to put the actual stabilizers in the water and dragging them through with the extra drag? So we quantify the number. We don't tell them, hey, you don't want to do this, you can't do this. We say, here's the cost. You decide whether you want to do it or not. We compared the curves to the design propeller curves for the engine and the shaft horsepower curves. And again, it's information for them to see to properly size their engine. We had one boat that was 300 horsepower, and he was maybe at 150 horsepower up at top speed. And he wanted a bigger engine. He wanted a 500 horsepower engine because he thought when he dragged the net, it was overloading his engine. I don't believe that's true, but we're actually going to put strain gauges on and measure it to prove it. This summer it's going to happen. What happens, though, when you oversize the engines, you can see your efficiency substantially goes down. So oversizing engines, additional maintenance cost, additional purchase cost, and additional fuel cost every year. So at the end of these surveys and the audits, we've been filling out this energy analysis tool for the fishermen. And what it gives for us is a baseline. Now we have this baseline and say, okay, now let's see where we should focus our energy. And this particular boat here that we're out there, it's a flash freeze boat. They have the freezer and they bring the salmon in and freeze it right away, so it's really delicious for us to eat later. And it is really delicious for us to eat later. We noticed that the refrigeration is actually the largest consumer of fuel for this boat. It's not the transit propulsion, it's not the fishing propulsion. And here's your hydraulic loads, and then your DC load is the green spot in there. So we decided, okay, we're going to do some energy conservation measures. I think it's pertinent for us, for this particular type of boat, that we look at some of the refrigeration. And that's exactly what we did. By the way, HVAC refrigeration, it seems to be one of the largest loads, whether it's on the Navy ships. You were on there, and we did an energy audit on a destroyer. Bath, Maine, December, the largest energy consumer was HVAC. I mean, it's ridiculous, right? Of course, and there's no real load there. It's just the way they're running. It's the culture. The Coast Guard, there are 3 or 4 cutters for them. Alaska, the largest single energy consumer is air conditioning in Alaska. I mean, it's not that the people are doing anything wrong. It's just the policies, the way things are set up, the design. We were just throwing energy away. So it's pertinent everywhere, I think, just to take a look at HVAC costs. We understand it better in buildings, but when we seem to get to a boat, we don't seem to do things. So again, heating and cooling at the same time, and wonder why we have such a large air conditioning load. So, getting back to the presentation, I want to just briefly talk about what energy efficiency is in terms of refrigeration or air conditioning. And the purpose of it is all we're trying to do is move energy, right, from one spot, in this case thermal energy, and we just need to transfer it or pump it over to another place. In the case of the freezer that we're working on, this is the freezer hold. Here's your compressor, and there's the ocean. That's where we're putting all the heat to. So it's simply the amount of heat we transfer over the amount of energy we put into it to move that heat. The less energy, the better off you are. So what can we do to actually help the fishermen reduce their fuel costs? The last boat we were on, I think the guy was saying he's running about $300-400 a day for his refrigeration to keep it running. So what are some of the basic things that we can do to optimize the system? One is reefer compressors are most efficient, highly loaded. These guys only have one, so it's not like they can shut one down because it's the only one they have. But what we can do is minimize the lift. And what I mean by lift, that's the difference between the suction pressure of the machine and the discharge. So the gas comes into the pump, which is the compressor, at a certain pressure, and then it pumps it up and it discharges it out at a higher temperature into the ocean to give off the heat. That's what we call the total lift. The higher the lift, the more power it takes that you have to put into that motor to go from this pressure to this pressure. It kind of makes sense, right? You're moving the same amount of energy, thermal energy, from this side over to the other side, except if you're going from here to here instead of here to here, it takes more energy. So we're looking at it, it's like, well, what can we do about it? Well, what we do is we decrease the discharge pressure by putting more cooling water flow through the condenser, and that lowers that lift down. When you do that, you can see your efficiency. This is from the manufacturer of the gear on top. So EER is the same as the COP. The higher lines are more efficient, the lower lines are less efficient. So when you bring that discharge pressure down, you reduce that lift, you can see your energy efficiency substantially goes up. On the ship I was on, it literally went from about 6 up to about 11 or so that we got. Significant change, just strictly by changing the operation of the valves. The other thing that happens is our capacity increases as you decrease the lift. So you're paying less money for it, you're more efficient, and you can actually, for the same unit, you get a greater capacity out of the machine. So instead of the guys going out and buying a bigger machine, if you can just get the lift down, you get significant increase in capacity. And what does that mean? At the end of the day, you save money, right, without doing anything with it. So now we've increased the capacity of the machine, we lowered the head down, saved them some money, but when we end up with extra capacity when you're in the low requirement mode, when everything's already pulled down, well then you end up with the unit cycling. So now we have capacity control that we have to deal with. I think I'm running slow here, so I have to go quick. This is that lift can go both ways. Some on the ships and everything, we bring up the suction temperature. We've had significant results with that as well. This is on a military sea lift command ship, where here's one way of operating it that I saw when I went on the ship, did the retro commissioning. Here's another way. This is the annual cost for running those, the AC plant. Just by how you're operating it, it's like $800,000 a year. Same equipment. So going back to how you can control the capacity, we have new technologies that are out there. Actually, VFDs have been around for years and years. But anytime you have a variable demand, VFDs work very well. So on the fishing ships, when you're putting all the fish in there, you really need to cool those holes down quick. So you need all that capacity. You keep your lift minimized, pull it down. But now you close it up and you got to come home. Now there's no load on that machine, so they start cycling all the time. And you can only cycle the machine so often. And cyclers turning it, they start and stop because there's no load to keep it running. What we do is we put a variable frequency drive on the unit so it slows it way down to reduce the capacity which it goes, on the one that we had it on, we were up about 10 kW to run the machine. We slowed it down and went to 4 or 5 kW at the low end. We're doing trials underway. We're actually putting the meters on board to physically document the savings from using this technology. As with everything with new technology, we need to be careful about how we install it. VFDs are great for these variable loads, but the issues that I've heard over the past with them not working right is typically from lack of following the manufacturer's instructions. Anytime you change power from one form to another for AC current, you have harmonics. You can see here's a nice clean sine wave, here isn't. So if you're looking at doing this, just make sure you follow manufacturer's instruction. Grounding is actually essential to be done the way they say to do it. So the other thing we found a lot of is a lot of these parasitic loads that are present all the time on the fishing boats. In this case, we could see the hydraulic pumps that are always connected and always turning. So you want to minimize all that. There's a picture from the EAT tool. And just by having the hydraulics, just turning, not doing useful work, was about $1,000 in fuel. And here's another one looking at the efficiency of hydraulic system. We're running a generator through an inverter. The actual useful work being produced right there is about less than a minute, but less than a minute, time thing. It was a little over half a kW, and yet the actual power going into the unit driving the pump was 10 kW. So you got less than 10% efficiency. And that's it. Thank you.